I'm Jared, the project manager.
My name is Chris Moreno. Patrick Poston. David Coons.
Our team's Fresh Air, our purpose of our project was to create mobile monitoring devices for the civil lab to determine if the air in the lab is dirty or not. First, we're going to have an introduction / background, and then we'll go into the body with our design criteria, architecture, status, milestones, and analysis. And then we'll have a conclusion with project status, expenditure status, and next steps and expected achievements. So we were given air quality monitoring devices that were Arduino based by Dr. Lautner, our client. We were posed to modify these devices for indoor use and outdoor to monitor air quality in the civil lab. First up, we have the user interface.
I was in charge of the user interface module. I was tasked to make a visual alarm to alert the users inside the lab what the current PM level is. Not only in the lab as a whole, but around each sensor. And this has been updated. It was originally 3 beacons. I dropped it down to 2 because there's no point telling them that they're safe to be in there. And then we added a 3rd beacon per request of our client outside of the room, so users outside know before walking in what the levels are in there. And then the sensor designation has been updated. Originally it was just 4 LEDs to let you know which sensors are sending PM, particulate matter. But I've updated that to 12 LEDs to classify which sensor is reading what level of PM.
I'm doing the ventilation and power module. The ventilation unit, the initial design was going to be hardwired to Raspberry Pi. Instead, I made a module where you're able to move around the room and connect it wirelessly over QTT. The relay I set to be normally closed in case I lose connection to QTT, which will automatically turn the fan on. The ESP32 GPIO 15 connects to the switch to ground. I had it connect to the other GPIO port, which made the code a little bit too hard, so I just had it set to high and it's looking for low. So I flip it, goes ground. Manual control. Initially has a push button. That did not help me that much, that's why I let go. It took the fan, changed it back to the other state. Instead I used the switch. The battery had a wrong JST pin on it, and I replaced that with the correct one so I can fit it into the power controller's housing. The 2 amp hour battery, I determined was not enough capacity for our usage, so I swapped it to a 4.4 amp hour battery. It's lithium ion, and I calculated it to last more than 6 hours. I gave myself more time. On for extended 30 seconds.
I was responsible for the PM sensor and communication module. All 4 PM sensor module circuits have been constructed and completed thorough testing. The PM data is now sampled every 5 seconds, and then all that data is sent to the control unit, including sensor IDs and PM data, instead of the 5-minute standard interval, because it was deemed necessary. The wireless transmission method has been changed to MQTT instead of Bluetooth. A router location in the civil lab has been determined for all modules to connect with Wi-Fi stably, and the cases have been designed and 3D printed.
So since the last time we talked, we were planning on using Bluetooth communication. Now we are using MQTT to make our wireless connections between microcontrollers. So that MQTT server is now being hosted on our Raspberry Pi microcontroller. And then we are also running scripts and providing a dashboard on Node-RED on that microcontroller as well.
So I was in charge of the data storage and data display, and as they spoke, we had to change to the way we receive messages into the dashboard. So obviously they said MQTT, as well as now, from last time we spoke, I'm parsing the data rather than receiving the data parsed from the main control unit, and retaining that information in 5-minute intervals and storing it into a database, as well as displaying an average of the data rather than the 5-second reset readings to ensure a more accurate, well-defined reading.
So for the power ventilation module, the power path controller, it has load sharing, output current draw of a maximum of 100 amps. It also simultaneously charges and allows operation of the microcontroller to take place at the same time. So if I hook up an external power source, I will also be able to charge battery while using that external power to run the microcontroller. And unplug it, battery switch over quick enough where it will not interrupt the microcontroller's data processing and sending it over to Raspberry Pi. The battery is going to be 3.7 volt normal voltage, it's a lithium ion battery. The 4 batteries cost underneath $30, which was the target I was aiming for. They'll also be chargeable. Some batteries are not rechargeable, but those are usually not what I'm looking for. And charge rate is about 0.5 C. And as I said before, 6-hour usage rate was my target to go, and I calculated out in the design report. For the relay module, I need something that's compatible with a 3.3 volt logic voltage on the microcontroller. It's also easy integration with the ESP32 was another aspect I said before.
So the criteria for the PM sensor module was that the sensor had to detect PM 2.5 and PM 10 as requested by the client. It had long lifetime and low power use for the battery to fully power it throughout the day. The microcontroller had to be compatible with our sensors interfacing method, which was I2C, has ample GPIO pins and it transmits via MQTT. Our LED had to be powered by the 3.3 or 5 volt rail from the ESP, and it's visible from long distance. The button closed the circuit only when pressed to deactivate the maintenance LED. And the breadboard had to be large enough to support all the components without interference.
So criteria for the user interface module, it had to be visible, highly visible from anywhere in the room, no matter whether they were really facing the front or the back. The audible alarm had to be loud enough to be heard over whatever equipment they're running at that time. The remote beacon must be activated while only dangerous levels are present. And sensor designation had to accurately display the PM density read by each sensor.
So very simply put, our Raspberry Pi 4B microcontroller needed to be able to integrate with all of our other modules. This included speakers for audible alarms, displays for the dashboards, keyboard and mouse controls, internet capabilities for our wireless communication, as well as enough I/O ports for the user interface.
And for the dashboard, the criteria was to display the real-time data on a platform that was preferably free, and then store that data so it could be accessed by who's ever using the lab, and both of those platforms being able to be remotely accessed on the host network.
So this is a diagram of our system architecture. At the bottom, you'll see our PM sensor modules. They read the data taken in the room. They're also connected to Davis module power. And then those are sent wirelessly to the control unit you'll see in the middle. And that makes a series of logical decisions based off the data, trips relays, sound speakers, the sensor designation. And the user can interface to that control unit by keyboard and mouse. The data is displayed on a monitor. And then ventilation is also tripped according to the PM level.
Here we have a room layout with PM sensors dotted around the civil lab. And we have a theorized detection capability of 4 to 5 feet, so it should be adequate enough to detect the entire civil lab. So the PM sensor and communication module, there will be 4 devices, and they will detect PM 2.5 and 10 in the air. They'll calculate the corresponding indoor air quality index based on the concentration. And then it will feature power path switching between an internal battery and wall outlet for power. It'll also feature a maintenance protocol with an LED to reset it via a button located within the case. and they'll be easily relocatable due to their compact size and power path switching feature. Here we have a hardware schematic to the right showing how the components interface with the ESP32 within this module. And then below we have a final design case for the modules.
This is a schematic of the ventilation. GeoPio 0 is being used, GeoPio 15 is being used, relays that are normally closed.
So the control unit, once it receives our sensor data, it makes our decisions based upon this chart we have here, categorizing it into healthy, unhealthy, or dangerous levels. This will communicate our data to any of the modules, including user interface, our data dashboard, and our ventilation modules. And this is just a simple diagram of how we've used the Raspberry Pi to connect to our user interface.
And this right here is just a sample of one of the tabs in Node-RED, which will have gauges to display the real-time data, and on the other tab it'll have graphs to show the real-time data. And also the files that are in storage can be exported via CSV, Excel, HTML, JSON, etc.
And then to the right of the dashboard, you'll see a fully integrated alarm system, the visual alarms. You see the beacons at the top, and then there's 12 LEDs towards the bottom of the tower for sensor designation, and there's also a reset toggle, kind of allow users to control the beacon. So project status, our final module testing has been done, everything has been integrated, it was semi-successful. We had a couple things we needed to iron out. These issues have all been addressed, and currently all the housing's been printed. The only thing that kind of remains is just soldering, getting everything put together.
So far, the deliverables to date have just been our projects, our presentations, and the posters needed. Our milestones. Our milestones so far have been that we've completed all design and calculation theory for each module. Design documentation for each entire module within the system has been outlined in detail. The components needed for the final design were ordered and have arrived. And also initial testing for crucial system functions has been completed. We changed to MQTT. We completed full system integration testing with minor flaws that have been addressed and rectified. And housings for all modules have been either built or 3D printed.
So our budget, we hit a total of $870 out of our $1,000 budget. We have our detailed payment structure for each member here. And then our achievements were basically that we delivered the product, we've had all of our successful testing implemented, and we just want to solve any of the issues that we had in our implementation testing, which are just some minor issues with the way our data is being displayed, and we want to deliver our product to the client. Any questions?
How easy movable is this? Like,
You can locate the PM sensor modules in any room that you would want. They're completely mobile and wireless. All they need to be is near a router, that's all.
so the base can be in, say, the civil lab, but if I wanted to bring the sensors over here, as long as it's on the same.
As long as on the same network, yes, it'll work. Yep.
As long as it has a stable Wi-Fi connection.
You're on the civils?
No, we're using a router to get Wi-Fi to the ESP32s.
And we are talking to IT tomorrow about getting on the civil.
Yeah, we're talking to IT tomorrow to get on the CIDL Wi-Fi.
Right there.
Has this been tested in the actual lab?
Yes, we've tested in the actual civil lab. That's where we did our last demo at.
Have you been able to see trends over time? If you do this or that, you get a certain level, so it's predictive?
We haven't tested for long-term use, as we've only been in the lab for an hour at a time for a demo, but that's a good point that you brought up we probably want to address.
Is there any harm in just running a fan the whole time and filtering regardless?
No, this can only help. It can only help. So you can, that's another feature of our ventilation unit, is you can manually toggle it on if you'd like to do so, or toggle it off.
The filters would just have to be replaced more often, but that's really the only risk.
Thanks.
Dr. Hain.
Can you explain to me how you're switching to MQTT, you said you started Bluetooth and then you went Wi-Fi, or what drove that decision?
Actually, in the software, they,
One of the biggest issues we saw with Bluetooth was there's a lot of devices on the proximity of the Citadel's campus. So when we were rolling through and we were testing for Bluetooth capabilities and connections, we saw a lot of MAC addresses popping up. And when we went into using MQTT specifically, we could set a username and password so that only our devices are accessing a specific network in order to provide our connection between devices.
Saw on your thing you specified 2 different sizes of particulate matter. How did you get to calibrating it to decide what size it was picking up?
So the sensor already detects PM1, 2.5, and 10 as is, so I just had to pull the data from the sensor itself and then use that in my calculation. Nick?
So how easily can you add another sensor? Like, is it set up like that right now?
Yeah, you can easily add another one. You can add as many devices as you like. We can even integrate a VOC sensor for that gas detection, but we deemed it was not necessary for our purpose. Dr. Dalton?
Going back to the MQTT, can you access the data from outside of the lab? Or do you need to be in the lab to access the data?
No, you can access it from anywhere within the host network as long as you're subscribed to the same topic that you're receiving the data from. So when Jared sends out the data in his sensors, he sends it out via a payload, and you have to be subscribed to that topic to receive that message all the same.
But me as a user, can I go and see the dashboard from like anywhere?
Yes.
Or do I need to be in the lab, or do I need to be
It's-
connected to the same router?
As long as you're on the same Wi-Fi as the Pi and everything else, you can simply go on your internet browser and type in the URL, and it'll pull up that as well as the data storage.
Which is why we're trying to meet with IT to get on the Citadel network so that you can access it anywhere on campus.
With this being deployed to an actual lab to determine human health and safety, are you concerned at all with any legal liability? That if that light isn't on, we're guaranteeing this is safe?
Well,
I've created the breakpoints to be, if it's under 100 IAQI, you should be perfectly safe. Like,
Should be.
also, they assume that risk going into the lab. I feel like that's kind of accepted before our product comes into play.
currently there's no product at all letting you know anything, so they're already assuming the risk.
Dr. Agarwal, do you have
Yeah, so is there any safety measures to protect your database from security hazards?
I mean, like, if it's encrypted, I mean, our database has a password you can able to access it.
That, as well as if someone wants to just include an entry or inject an entry that says it's an unsafe PM level, how would the system protect it? It will just say, okay, lock out the lab, everyone come out of the lab.
really just the structure of our code, the way we're receiving the payload, it's formatted a certain way, so they have to know the exact format, on top of knowing the topic that we're subscribed to, and the format of the payload, and then we also have username, password for our router, for MQTT, as well as InRed. So there's a few safety features, nothing to stop anybody from injecting anything, but odds are if they try to send a message, it won't make it to anything else, because it's not formatted the way we're looking for it.
With MQTT, you are sending data on Wi-Fi.
Yes.
If I have a packet sniffer online, right, I can sniff your packet structure and just send another packet, like a repeat attack, and say, okay, just send the PM level as dangerous, right?
Yes, sir.
And that way I can just stop a practical in between.
I suppose somebody could do that. I don't know why they would want to, but
Now the question is how to protect that.
yeah, I guess we'd have to encrypt that messages that we're sending in some fashion.
On top of that, I ran my code for the ventilation unit to detect the state change. So if they manage to block the sensors from even updating on or off, that's gonna be a big issue. But if they don't block the sensors from sending data to the control unit, my ventilation should still look for a change of state. So if somebody like sends a fake on from their computer, well, Raspberry Pi is going to send me off from the sensor, so the ventilation will turn off. So it ain't going to be always on.
All right, thank you guys.
Thank you.